So, here we will first let us calculate the concentration of the gaseous reactant C A, because it is mentioned that question 8% of the in the atmosphere of the 8% oxygen stream, gas is the 8% oxygen stream. So, concentration will be P A by R T. Here pressure, total pressure. So, 8% oxygen is there. So, with that in the air 8, sorry, 1 minute, eraser. Now, it is the scale. Okay. Which one is eraser? This one. Okay. Yes. So, it is 0.08, 8%. So, 0.08 into it is total pressure is 1 Pascal, that is 10 to the power 1 bar atmospheric pressure if you take, that is 10 to the power 5 it is given, pressure 10 to the power 5 Pascal. So, 8% of the that is the oxygen pressure. So, 0.08 into 10 to the power 5 R gaseous constant, that is 8.314 into T is the, as it is temperature is mentioned 900 degree centigrade, in the Kelvin 900 plus 273. So, thus this is coming calculating 0.820 moles per meter cube. Now, molecular weight of the zinc is given, means you found out, that is 97.45. That means, we can say that it is this much grams per mole. So, we can say that this is gram per mole. Sorry. So, molecular weight as 97.45. So, we can say concentration is the that is this is 97.45 gram per mole. Now, or we can say that is will be kg per mole if you express 0.09745 kg per mole. So, okay, let me erase this concentration of the gas. We already noted down. So, just so this is in kg mole, if you convert, it is point. Zero 0.09745 kg per mole. So, thus we can calculate molar density of the pure that is solid or solid reactant. Molar density rho b, density is given, that is density divided by this kg moles will give you the molar density. So, density is 41 rho s divided by molecular weight in kg molecular weight, or you can write. So, 4130 divided by your 0.09745. Okay, this is molar density is coming 42,380.71. So, we can write 42,381. Okay. Now, from the reaction where we have written the moles of the solid, that is zinc sulphide, is 2 by 3. It is there in the question. So, thus that is B, which is moles of the solid 2 by 3. That is number of moles of the zinc sulphide. Molar density we got 42,381. Now, using this we can calculate now the overall reaction rate. So, let me erase this. Now, first bit in the question, it is asked that to assume that reaction proceed by the shrinking core model, calculate the time needed for complete conversion of the solids and find the rate controlling step. Now, here in the shrinking core model, the reaction rate is given by overall reaction rate, which is 1 by k bar equal to 1 by k c reaction rate constant plus dp by 12 ds, which is ds means it is diffusivity. You can write in this way, d diffusivity ds diffusivity. So, now you substitute particle size is given, diffusivity is given, now reaction rate constant K c is given. So, substituting we can get the overall reaction rate, that is k bar. So, k bar will be 1 by 0.02, because K c is given 0.02 meter per second, rate constant is given. So, plus here dp is given 2 mm. So, 2 into 10 to the power minus 3 divided by 12 times diffusivity. Diffusivity is also given 8 into 10 to the power minus 6. So, 8 into 10 to the power minus 6. So, calculating this is coming 1 by 50 plus 20.833, means 1 by 0.02 is 50 and this is 20.833. So, thus this is coming 0.0141. This is the meter per second. Now, the reaction rate constant, overall reaction rate we got 0.0141 meter per second. Now, resistance to diffusion through the product layer is here, because see second term in the denominator contains the diffusivity, that is as it is again in the second term in the denominator contains the diffusivity, and it is 1 upon term is there. So, it is the resistance offered by the diffusivity. So, resistance which is offered by the diffusivity is important through the product layer is nearly as important as this reaction rate constant was 0.02. So, 1 by 0.02 is 50 and this dp by 12 ds, that is it is coming 20.833. That means, this 50 is the resistance offered by the reaction rate and this is the 20.833 is the resistance offered by the diffusion. So, as in the morning we had discussed, no reaction is completely ideal, that is follow the shrinking core model or no reaction follows the uniform reaction model, because uniform reaction model means only the diffusivity will be controlling the reaction and shrinking core model means only the reaction rate will be controlling the reaction. So, as here both are equally important, because 20.833 means nearly 21 in comparison with the 50, it is not negligible, although small, as it is not negligible. So, we can conclude that here both are important, means both offering the resistance to the reaction, whether it is 20.83 means diffusion rate or the reaction rate, both offering resistance to this reaction. That means, the actual reaction is following in between the shrinking core model and uniform reaction model, followed, because by seeing these two numbers 50 and 20.833. This second term in the denominator is because of the diffusion resistance, first term in the denominator is because of the reaction rate, because Kc is the reaction rate constant. And now, we have to find out the, as in the question it is asked that time calculate the time needed for complete conversion of the solids. So, for complete conversion of the solids we can find out the time now. Let me erase this part. This is followed how the reaction is model is fitting, because it is neither completely the uniform model or the reaction model or the shrinking core model. Okay. So, the time required for complete conversion we have to find out. So, it is time needed for complete conversion and it is given by tau is rho b into r divided by b K C C A, where B is the number of moles of the solid reactant, K C reaction rate constant, C A is the concentration of the gaseous reactant, and rho B density molar density already we have calculated C A rho B, and B is known in the reaction, it is B is the 2 by 3 and R is the particle size, that is radius, diameter is given. So, half of that we can take. So, now substituting we can calculate the total time. So, here rho B already we have calculated, it is 42,381 into reaction into the particle size, that is the radius of the particle. Here it is 2 mm is the particle size, dp is given. So, it is 1 into 10 to the power minus 3 meter. So, divided by here your number of moles B is 2 by 3 into Kc reactant reaction rate constant, which is 0.0141 . Sorry, it is the K bar, not the Kc. Reaction rate, which we have calculated 0.0141 meter per second and into the gases concentration of the gaseous reactant, which we have calculated 0.820. So, calculating, this is coming 5498 second. Second, converting, that is 1 hour 31.64 minutes. Okay, this much time is required for complete conversion of the reactant. So, first bit over, clear? Just we first in what is required, that we have to write down, then we can calculate. Calculation is not difficult. So, second bit we will be calculating. I am rubbing it. B. Repeat the calculation for particles of size dp is 0.1 millimeter. So, here we will compare, morning we had discussed that fine particles follow the uniform reaction model and the coarse particles, bigger size particles follow the shrinking core model. So, that here we can whether means it might not be completely following the uniform reaction model or shrinking core model, but it should from the calculation we can see that whether it is nearer to uniform reaction model or not, because particle size is small. Here dp is 0.1 millimeter for the second bit. 0.1 millimeter is given. Or it is 1 into 10 to the power minus 4 meter. Now, that means R is 0.5 into 10 to the power minus 4 meter, radius is. Now, the k bar we can calculate using the same formula. Already molar density we know, and molar density afterwards we can calculate. Diffusivity is given, reaction rate constant is given. So, using the same data we can calculate. It is coming 1 by means first term remaining same, because reaction rate constant same, 1 by 0.02, first term in the denominator. Second term, it is dp by 12 ds. dp is 1 into 10 to the power minus 4 divided by 12 into diffusivity, which is also same, 8 into 10 to the power minus 6. So, this is, if you calculate, this is coming 1 by 50 plus this term is coming 1.042. And it is 1 by 51.042 or this is equal to 0.0196 meter per second. In these two terms in the denominator, you see one is 50, another is 1.042. 1.042 means diffusion is not controlling resistance, diffusion resistance is negligible in comparison with the reaction rate resistance, because reaction rate which is offering the resistance, that is high, means resistance is high, reaction rate resistance, that means it is controlled by the diffusion. So, resistance by the diffusion is less, 1.042. So, as it is the resistance is less by the diffusion means controlled by the diffusion, resistance is more by the reaction rate. That means, when the diffusion is controlling, resistance by diffusion is less. So, it is the uniform reaction model, and that morning also we discussed, that is fine particles follow the uniform reaction models. So, it is nearer to that, not completely, because completely means this term could have been 0, resistance term could have been 0. So, thus it is just we found out overall reaction rate as the 0.0196 meter per second. Now, similarly for the time for the complete conversion we can find out. Tau, which is the same formula, we can it is the rho b r divided by b k dash into C A. So, density, molar density remaining same, 42,381, only your R is varying, that is 5 into 10 to the power minus 4, sorry 0.5 into not 5, 0.5 into 10 to the power minus 4 divided by B is 2 by 3, your overall rate constant it is coming 0.0196, 0.0196 into C A, that is 0.820. So, this is coming 197.77 second. So, thus we can say 3.2962 minute. So, with the size difference, see everything else remaining same, you can see for the size difference here for the larger size, that is 2 mm particle size, the time required is 1 hour 31.64 minutes, and for the 0.1 mm which is 1/10 of the 1/20th of the particle size, for that it is only 3.2962 minute. Hello. So, naturally the fine particles means uniform reaction model, and it will be quicker, the reaction will be completed. So, another example, just we can do similar to this. Question perhaps I have not written. Time, calculate the time required to burn to completion of completion of the particles of graphite. Graphite is taken here, the same type, similar type problem, only here instead of the zinc sulphide, here graphite is taken. Graphite means carbon. So, molecular weight or the atomic weight, here we can take 12. So, when molecular weight is 12, that means 0.012, you can say gram moles will be 12 gram per mole, we can say this is kg moles if you take 0.012 kg. And if you take particle size 1 mm, dp if you take 1 mm, and density of the solids 2200 kg per meter cube, reaction rate constant Kc is 0.2 meter per second, 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 0.2 me and assuming overall reaction rate also same. If you assume that rate constant and overall rate constant is equal, so again assuming here the same environment, that is 8% oxygen is provided, where the pressure is 10 to the power 5 Pascal. So with that we have to, here it is found out time required for to burn the entire graphite particles completely. So here we can calculate rho b, because here k bar is there, kb we not k bar is not required to calculate. Only thing that as here tau contains the tau to be calculated using rho b. So we can just rho b first we can calculate, that is density divided by molecular weight in the kg. So rho b we can calculate 2200 divided by 0.012. So this is giving you 183 183,333 this much moles per meter cube. Molar density is there. Now tau we can calculate. Another thing, here the reaction will be, graphite means carbon, oxygen will give you carbon dioxide. That means here the small b is the number of moles of the solid reactant. So small b is 1 here. In the previous reaction it was 2/3 zinc sulphide. So here the reaction will be, it is carbon plus a complete combustion. So carbon plus oxygen giving the carbon dioxide. So B is 1. So thus we can calculate the tau. Rho B, which is 183333 divided by rho B into dP. dP is given here, that is 1 mm. So 1 into 10 to the power minus 3 divided by here B into k bar or kc, here it is equal into Ca. So it is, if you substitute, one into Kc, which is given 0.02, sorry 0.2 into here Ca, already same environment. So which is concentration of the gaseous reactant, already it is in the first example we calculated. So it is 1 into 0.2 into 0.820. Sorry, another thing is there, it is R, na? Not the rho B R, not dP. So here we have to divide by 2. And the tau is the rho B R. So divide by 2 means here we can multiply by 2 in the denominator. Okay? Rho B into R, not the dP. So thus it is coming 558.9 second, 558.94 second, or it is 9.3 minute. It is clear? Just we can here tau we calculated, and the as it is the 1 mm size, here it will be coming again in between the two reactions, because we saw that point 1 when the particle size is 0.1, it is more towards the shrinking uniform reaction model, and so if it is in the middle, it was the 2 mm, then half of that. So, it will be middle of the two models. So, shrinking core model, two examples we just solved. One just another example we will be seeing. Sorry. Okay. PPT will let us share. A feed consisting of the two sizes, when the size distribution just little bit I mentioned in the morning hour, during the fluidization how size distribution changes because of the fluidization, particles moves up and down, attrition occurs because of the rubbing or the attrition of the particles, particle size reduces, and thus when the more fine particles are created, then the size distribution changes, and again with when we go on fluidizing at the same flow rate, fine particles will be moving upwards. Moving upwards, they may be carried over, that is the entrant may be entrant. If fine particles are carried over, more larger particles will be in the bed only. So, there also size distribution changes. So, thus just to have the some idea about how to find out what will be the that is size distribution, or the just small examples will be solving, and detail part as we have not discussed. So, other detail program with the data, detail problem with the data of the size distribution we cannot solve here, that will take time. Here feed consisting of the two sizes of the solids to be treated in a pilot plant fluidized bed. If the feed mixture containing two sizes, the solids remain unchanged in the size and the density, and elutriation occurs. Elutriation means separation in the bed only. That is bigger, two sizes are there, the bigger size will remaining in the bed, smaller size will be moving to the freeboard region, from where it may go outside or remain in the freeboard area also. That is the elutriation. Entrainment means elutriation will occur, followed by carryover of the solids out of the bed, that is the entrainment. So, elutriation occurs, that means size separation occurs. Find the composition and the flow rates of the entrained and the overflow streams, as well as the mean residence time in the bed for the two sizes of the solids. How much time they are remaining in the reactor, because residence time also has impact on the reaction rate. So, that is why it is required to know the what is the residence time. How the size distribution part we will not discuss, just residence time part we will discuss with one small example. Yes. So, just I am drawing one figure, and then we can Just small example, so it will not take much time. Now, suppose a just fluidized bed is like this, lower part I am not. During the fluidization, when fluid is supplied, a mixture of particles are here, some are of the bigger size, some are the smaller size, suppose like this during the fluidization. Now, here suppose here also we can say that this is the freeboard region. Here the main bed region, where the main bed completely we cannot say, more than the main bed region also, because particles when fluidized, but this is the freeboard region where only fine particles are going up, crossing some boundary, they are moving up, that is the freeboard region. Now, from freeboard region some particles will be carry over. If you see, some particles go outside, that is the, and if your feed is F0 and here overflow, that is F1. Here F0 is 2.7 kg per minute, consisting of both coarse particles and the fine particles, and here overflow is 1.7, data given F0 2.7, F0 the of fines, from this 2.7, 0.9 is the fines kg per minute, naturally coarse will be 1.8 in the coarse particles, larger particles, and bed weight is 17 kg initially taken. K of fines, it is given 0.8, K of coarse, rate constant you can say, coarse, it is given 0.0125 minute per minute, actually it is per minute. And when the separation illustration is getting occurred, coarse fine particles going to the up, here this also contains some fines, mainly some fine, more fines and the coarse. So, here F1 F2, this is F2, this also contains fines and the coarse, and this also contains fines and the coarse. Only when size distribution occurs means percentage will vary, whatever is in the feed, its variation will be there in the overflow and the carryover solids. So, here as per the question, two sizes is to be treated in a fluidized bed reactor, the solids remain unchanged in size and density, illustration occurs, find the composition and flow rate of the entrant and the overflow. This is the entrant solid F2, overflow is the that is F1, feed is the F0. So, as well as the mean residence time in the bed of the two sizes of the solids, fine particles how much remaining in the bed, how much time, and coarse particle how much remaining in the bed. So, followed. So, here we can balance it F0 if with respect to fine, if you do the balance, that means F0 fines will be F1 fines with respect to fines F1 plus F2 fine, sorry, this is the F2 fines. Similarly, with respect to coarse, F0 coarse will be F1 coarse plus F2 coarse, means total coarse particles whatever is the in the feed, that is distributed in the F1 and the F2. Similarly, whatever fines is there in the feed stream F0, that is distributed in the F1 and F2. F1 is the that is entrant solids, overflow solids means product which we are collecting. F2 is the we are not collecting, it is automatically going out. If required, we may provide the cyclone separator to separate that, but F1 is the overflow that we are collecting. So, here we have to find out this how much time this both F1 and F2 means coarse and fine particles remaining in the bed. So, this part clear. So, I will just solve the it is small example. So, I am rubbing this. So, with respect to coarse also you can write F0 coarse equal to F1 coarse plus F2 coarse. So, when we are solving this, one equation is there which is suppose no means if you find out means finally we will collect everything means F2 and F1. So, then collecting everything na, that will be after entrainment we are collecting the other things. So, that way we are column after the experiment gets over. So, to find out what was the size distribution. So, here one it is F1 equal to, if we write summation of I equal to 1 to 2, because two particles are two sizes are mixed here, will be we can write it is F0 Ri divided by 1 plus W by F1 into K Ri, where the K is the reaction rate. So, Ri for any particular size if you write, if you first, so that means if you expand this, we can write this as instead of summation, we can write, if you expand this will be F0 R1 by 1 plus W by F1 into K R1. This you can write plus F0 R2, wherever I is there, that is only two sizes are there. So, 1 2 we can separate. So, F0 R2 divided by 1 plus W by F1. In the formula it is F1 is there in this. So, this will remain as it is, only this K of R2. Followed. So, it is K of the fines and the coarse, K of the F1 if you R1 if you take fines, K of fines is question given 0.8, we can write 0.8, and K of coarse, that is R2, K of R2 coarse particles we can take as the R, K of R2. So, thus we can substitute now, which is F0 R1, that is fines is F0 of R1, in the feed it is 0.9 is there. So, 0.9, let me rub this, I am not on the top, I think. So, this we can write as 0.9 divided by 1 plus 17 by W is the total is the 17. So, 17 by F1, now F1 is unknown into 0.8, K of R1 is 0.8 plus that is F0 R2 which is 1.8 divided by 1 plus W by F 17 by F1 into K of R2 which is 0.0125, all right. So, calculate here by trial and error we can find out the value of the F1 because we can here 3 terms all containing the F1. So, just by trial and error we can find out. So, it is F1 is coming 1.7 kg per minute. Now, putting this value we can get, if F1 finds we are getting, so it will be F0 finds divided by 1 plus W by F1 into K of finds, means only first term. If you this is the mixture we have taken 2 sizes. Now, if you here you write only for the finds, the equation will be modified for one particular size only. So, if you write the same equation for the one size, so F1 of finds will be F0 of finds divided by 1 plus W by F1 into K of finds. The first term will be equal to. So, here because it was summation we had taken for 2 sizes, now for 1 sizes we are taking. So, thus here substituting, here F1 we can substitute. So, which 1.7 we got, putting the value in this equation. So, similarly F1 course here we are getting F1 finds as this F1 which we got, it is the total F1 for both the sizes. Now, only for finds if you substitute F0 finds which is 0.9 divided by 1 plus 17 by F1 which is 1.7 we have got into K of finds which is 0.8. So, this is coming as 0.1 kg per minute. Similarly, F1 course we can calculate, which is or you difference also you can take and we can check also it is. So, F1 course similarly calculating, that is F0 course divided by 1 plus W by F1 into K of course particles, that is 1.8 divided by 1 plus 17 by 1.7 into 0.0125. So, this is giving 1.6. So, it is coming 1.6 plus 1.7, F1 already we have got by trial and error as 1.7. So, this is matching. So, it is all right, kg per minute we got. Now, we can get that is F2 finds, similarly F0 finds, F1 finds plus F2 finds. So, just when F1 finds and F0 finds we got, now F2 finds we can get. F2 finds, which is F1, F0 finds minus F1 finds. F0 finds already known and we have calculated F1 finds. So, this is coming 0.9 minus 0.1, which is 0.8 kg per minute. Similarly, F2 course also we can find out. Course, which is F0 course minus F1 course, which is 1.8 minus 1.6, which is 0.2 kg per minute. So, adding we can get F2 we are getting 0.8 plus 0.2, which is 1 kg per minute. Already we have found that also. So, it is the mean residence time we can calculate now. So, mean residence time T of finds, because finds and course how much time they are residing. So, it is in general the formula is T of R, whether course or the find, 1 by F1 by W plus K of R. K of R means whether fine or coarse. So, T of fine will be 1 by 1.7 F1 by W 17 plus K of fines, which is 0.8, that is coming 1.1 minute. Similarly, T of course 1 by F1 by W 1.7 by 17 plus K of course is 0.0125. So, this is coming 8.9 minute. Alright, residence time we got for the coarse particles and the fine particles. This is a small example. Actually, for wide size distribution we need the lot of data, that will take long time also. So, that we are not doing. If time will be there we will do, otherwise just in the detail also in the theory we did not cover, just overall I just covered. 1 hour time what is required, that I just this is clear. So, this way we can find out the how much time particles are residing within the reactor.